Let's talk about the basics of torque. So here we have a system of a beam that's attached to this hinge over here, and the beam therefore can pivot back and forth either counterclockwise or clockwise. We'll ignore gravity, and you can see that there's two forces that are being exerted on the beam. One of those forces is out here on the outer edge, pulling straight up at this moment in time, and the other one is pulling down right in the middle of the beam. And they both have a size of 2 newtons. Now the length of this beam is 6 meters, and what we're going to learn how to do is calculate the torque that's exerted from each one of these forces, and then what's called the net amount of torque that's being exerted on this beam. All right, so let's get into it, and I'll show you first the basics of how to calculate torque, and then we'll kind of finish up with what's going on in this particular problem. All right, so here is how we calculate a torque. And before we look at some of these formulas down here, let's just try to make it as simple as possible. These are the 4 steps that you need to do. So step 1, pick a fixed point anywhere in the universe. Now there are better choices than others, but it really actually doesn't matter where you pick your first point in principle. But I just picked a random point over here, so there it is. Then number 2, draw a position vector from the point we chose to the location of the force. So we can see we have a mass m over here, some ball or something, who cares? And there's a force exerted on it up and to the right at this moment in time. And so we'll calculate the torque that that force exerts on the object about this fixed point. Now that was a lot of language, right? I'll say that again. We're about to calculate the amount of torque that this force exerts on this mass about this fixed point. All right, so let's do it. We'll come over here, and the next thing we have to do is draw a position vector from the point to the location of the force. So we'll do that. It's just a straight line that has a directed arrow on it to the right. That's the position vector, and often, or we do call that r. So, and it's a vector, and the force is a vector too. So I'll make sure to put a force for a vector symbol above that. All right, so easy enough so far. Number 3, calculate the amount of force perpendicular to the position vector. All right, so now what we have to do is realize that, this line here that we've just drawn, or this position vector, if we kind of extend it out further, just to give a helpful visual aid like that, right? There's this infinite line that can be drawn like that, and we want to figure out how much of this force is directed perpendicularly to that line. Now, it shouldn't be too hard to see here that you would drop down a vertical component like that, and that would be how much of that force is directed perpendicularly to that line. And so I'll call that force perpendicular. Okay? Now, in order to actually get the value, we would have to have some information about angle. So you could imagine maybe coming along and somebody specifying this angle. And if they did, well, then force perpendicular would easily be just F times the sine of that theta right there. However, what if somebody came along and actually specified a different angle, maybe like this angle or something? Well, then you'd have to do the math correct and do your right triangle trigonometry and make sure you get the correct angle. So you just need to be careful with what angle this is in this formula down here. The key idea that you need to do with the force vector, so you'll always get these things right when you're calculating them, is just remind yourself over and over again, I need to pick out the component of the force that is perpendicular to this line that's been drawn from the fixed point over here. As long as you keep remembering that, you'll be able to kind of check whether or not you got it. All right, now continuing along, once you've done that, then you just multiply. Multiply the length of the position vector by the perpendicular component of the force. And that ends up looking like this when you just write it out. R times force perpendicular. Cool. So if we had numbers on this, maybe, I don't know, this was 6 meters or something like that, the distance. And then what if this angle theta was 30 degrees? And then what if the force value, the magnitude of the entire force, I don't know, we just make something up, was 10 newtons. Okay. Then what we would do here is we'd plug in our 6 meters for R, and then that perpendicular component of the force would be equal to 10 times the sine of 30. Sine of 30 is a half, so get 5 newtons there. And this would be positive 30 newton meters of torque. That is exerted by the force about, and then we can give this point a name, call it point P, about point P. All right. So the 10 Newton force exerts 30 Newton meters of counterclockwise torque about point P. All right. Now the directionality of these things, how can you tell it's counterclockwise? Um, well, you can see how this force is kind of directed up into the right, right? Kind of imagine it like this. Like let's say you had a beam or something and you pulled uh, totally perpendicularly like that, right? And you have this beam that had like a hinge over here. Which way would this beam tend to rotate? Of course, it would go counterclockwise if you did that. Now, there's a more technical math way to get the direction that I'll show you, but hopefully you can see how it's positive and counterclockwise. All right, now let's go back to our original question. Here's this beam, and imagine just we're out in space or something. There's no gravitational field to worry about. The beam is 6 meters in length, and we want to calculate two torques. The torque that's exerted from force 1 and then the torque that's exerted from force 2 about point P. So we're choosing point P as our fixed point, and then we'll try to interpret the results. All right. So kind of before you try to imagine what this beam is going to do, like how it's going to move, let's just be very clear in the procedure on how to calculate the torque from each one of these forces. So pause the video, use what we have just talked about, and see if you can correctly calculate both the magnitude and the direction, clockwise or counterclockwise. And remember that counterclockwise is positive and clockwise is negative. Get the direction right there. And see if you can find the torque from each one of these forces over here. All right, pause the video, give that a shot, and then we'll take a look. All right, step one, we'll calculate the torque T1. And so we follow the procedure. We draw a position vector from our chosen point, our fixed point P, out to the location of the force, just like this. And I'll label that as vector R1. Now the distance of that is going to be 3 meters because I told you that the beam was 6 meters in length. Awesome. So now we can come over here and calculate T1, or sorry, I should say torque 1, about point P. And it's just R1, 3 meters, and then multiplied. And you might be wondering, okay, so what do I plug in here for the force? And you can see how that force is going to try to cause a clockwise rotation of this beam. And so you could, if you wanted to, put in the minus sign, minus 2 newtons, like this, which agrees with the fact that the force is down. That's fine. And then you're going to get a minus 6 newtons per meter. What I tend to do is just plug in the magnitude of the force there and then just look at the problem and see if it's going to cause a clockwise or counterclockwise rotation, and then kind of put the minus sign out at the end manually like that. Either way will work here. But there you go. And then for the other one, torque 2 about P. We're going to do the same thing. I'm going to have to draw up a little bit. So you want to start your drawing right at the point. Oops, not drawing a very good straight line. But there you go. There's R2, and that's 6 meters. So notice, this is really important. Notice how force 2 is twice as far away. Let's see the impact of that mathematically. So we get 6 meters multiplied by positive 2 newtons, and we get positive 12 newton meters of torque, or that would be counterclockwise, and then this, of course, would be clockwise torque. Great. Now we're in a position to interpret what this all means for the beam. So go ahead and pause the video and maybe write out on your paper, what do you think this beam is going to do? How will it move? Let's just assume that it starts at rest and it is physically attached to this hinge over here. So it must rotate about that hinge. Doesn't have to be the case, by the way, to calculate the torques. You absolutely do not have to have something like physically attached. You can always just calculate torque as a fundamental um, term or something, right? But pause the video and see if you can figure out which way you think this thing's going to go. All right, go ahead. All right, well, if you said counterclockwise, then that is correct. And the way we approach this is we need to calculate what's called the net torque. And if you know how to calculate a net force just by summing up all of the individual force vectors using vector addition, then you know exactly what you're doing here with net torque. Now, for us, luckily, we're not going to have to get bogged down in vector addition with torque. Instead, we're just going to be dealing with situations where either there's going to be a clockwise torque or a counterclockwise torque. And that's effectively like a one-dimensional idea. Even though the object itself is probably moving in two-dimensional space, the fact that you can only go clockwise, that's like one way to move, or counterclockwise, another way to move rotationally, that effectively mathematically is like a one-dimensional type of thing. And so we can just use positive and negative signs to add up our torques here. So therefore, we can come along and we don't have to get bogged down with the vector symbol and everything. We'll just write down that we have torque 1, okay, that's negative 6 newtons times meters, and then we have plus 12 newton meters, giving us a net torque of positive 6, or a net counterclockwise torque. So we'll label that the net torque. Awesome. All right, now you're probably wondering, great, so how does that help us understand what this beam is going to do? All right, well, let's talk about that now. All right, so let me focus your attention down here at the bottom first. And you know that net forces are what cause linear acceleration. So if we have a mass here, maybe starts at rest, doesn't have to, but if you exert a force on it, imagine this 4 newtons is the net force, then this mass will accelerate, and the rate it accelerates is directly proportional to the amount of the net force and inversely proportional to the mass of the object, all related through Newton's second law. So in a very similar way with torques, torques cause not linear acceleration, but this new idea we've been thinking about called angular acceleration. So what we will now see, and I've drawn out a beam here, imagine it starts at rest, and then we continuously apply this 4 Newton force, but notice how this 4 Newton force actually rotates along with the beam itself and always stays perpendicular to this straight line that's drawn from a well-chosen point right here at the pivot. You can see how there would be a constant torque. Let's just actually solve for that real quick to make it concrete. So imagine this was 2 meters, right? Then the torque exerted by the 4 Newton force would be equal to 2 meters times 4 newtons, and this would give a counterclockwise torque, and so that would be 8 Newton meters, or counterclockwise torque. And what you can now see is that this torque would be responsible for spinning this beam around counterclockwise, and the rate at which it moves angularly, the rate at which angle is swept out, okay? You can imagine as we watch the beam go around, we're going to be sweeping angle out as we continually go around and around, right? The rate at which that angle is being swept out is increasing and increasing and increasing as time goes by. Omega, the angular velocity, would increase in this case. Now, it doesn't have to increase in general. It could decrease. If you already had it spinning up, for example, and then you applied a clockwise torque, then you could slow the thing down. But we'll talk more about those ideas at a later time. Anyways, the angular velocity can change via the application of a net torque. And the way that this gets consolidated in a formula is in a very similar way. So you add up all the torques, and that's going to equal You might wonder, what does it equal? Well, angular acceleration is going to be over there. That's true. But then we also have this um, new term, I, and we're not going to talk about that today, but it's called rotational inertia. Rotational inertia. It plays a very similar role that mass does, except there's some more subtleties about it. It's kind of, how hard is it for this object to rotate around some chosen point in space? And then that becomes a number, and then we're able to calculate things. Okay. But by the way, this analysis is kind of a simplistic analysis for rigid body rotations. When you get to some more higher level stuff, then there's some other things that go on that I don't want to talk about right now. But anyways, for our purposes, this looks great, and we're going to come along and we'll be able to then say that the angular acceleration will be equal to the net torque divided by the rotational inertia. All right, so I'll put a box around this, and then a box around that. Great. All right. Now, to kind of finalize this video, I want to share with you a situation that does not involve any of this angular acceleration. Like I said, in the future, we'll come back to um, solving angular acceleration problems when we have a little bit more knowledge about this idea of rotational inertia. What we need to do first, however, is talk about kind of some more simple systems where you have what's called static equilibrium, where there's a constant angular velocity or usually no angular velocity at all. So the system's at rest. But you have all these forces which give rise to all these torques, and everything balances out. You might have seen this before, like on a seesaw, or pretty much everything out in the world that you look at is going to have different forces being exerted on it and different torques, and it all sums to zero. So let's take a look at that now. I'll give you some nice challenging problems where you'll be able to apply what you learned about how to calculate torques. So let's give it a shot. All right, so here's another example. Very similar setup. We have a hinge, call that point P. That'll be our fixed point that we will choose. And the beam is 3 meters in length. There's no gravitational field to worry about here. And we have the application of two forces, F1 and F2, and their directions are shown. My question to you to start with is, will this beam angularly accelerate? And if so, which way? Go ahead, give it a shot, pause the video, and see if you can get it. All right, so here's the whole analysis. We add up the torques, torque 1 and 2, and we calculate the first one. So we draw our line, straight line position vector, and that's going to be 1.5, multiply that by -8 newtons, gives us -12 Newton meters. Do the same thing here. 3 times 3 is 9, so it's a positive or counterclockwise torque. Add them together, and it looks like we get minus, not 4, that's actually -3. All right, so I fixed that, and it's a clockwise torque, and we could then find the angular acceleration. Notice I didn't give you the rotational inertia because we haven't really learned that yet, but if you knew that number, you'd be able to divide, and then you would know the angular acceleration, or how many radians per second squared this thing changed its angular velocity at. All right. So this would not be a fixed situation or a constant angular velocity situation, or what we call static equilibrium. But what I want you now to do is make it a static equilibrium situation. And in order to do that, I'd like you to change the value of force 2. So figure out what you'd have to modify the size of force 2 to be such that the beam didn't move at all. You're not able to change force 1, and I will also not allow you to move the forces to different locations. Of course, you could theoretically move these anywhere you want, but for now, force 1 will be locked here at this position, force 2 will be locked here at this position. So go ahead, give it a shot. Hopefully it's pretty easy, but figure out what value must force 2 be so this beam doesn't rotate at all. Give it a shot. All right. So hopefully you figured out that it would just have to be 4 newtons, because mathematically 3 times 4 is 12, and then that'll cancel out with this negative 12 right here. Now, you probably figured that out just because of the math, but take a step back and let's try to process that a little bit more conceptually. I mean, really stop and think about what's going on here. We are pulling down at the middle of the beam with twice as much force than way over here. See that? Like, imagine if like there was this heavy beam, right? And it was attached maybe to a wall in your house or something horizontally, right? You got this beam, it's attached to some wall and it can rotate because there's a hinge. And you are responsible for keeping the beam level, right? You can do this actually with pretty much any object in your house, like a kind of like a long object, maybe like a meter stick, or I don't know, you got something that can, extend out. And if you want to support that thing and hold it so it's horizontal, you don't hold it at the middle. You don't hold it close to the pivot point. It's really hard to do that, right? Where do you naturally hold the object as it extends out? Well, you're gonna come over here and you're gonna apply a force right at the edge. And this whole 3 meters gets to play this wonderful role mathematically because it multiplies times the force that you exert over here, and that gives you a lot of torque. It really helps balance out other torques that are pulling down clockwise, so you can keep this thing straight and level here, right? So the farther and farther you go out, I mean, imagine, um, yeah, like either like a really long beam that went way out, right? If you can apply a force upwards at the edge of the beam, you get like a lot of torque for that, and you don't have to apply as much force as you would at different locations. Um, I guess maybe a secondary question that we could ask would be, what if we started to move this force inwards more? Let's actually do that. Let's go ahead and change the position of this force. Why don't we change it to half of a meter and see what happens? All right, so let's pause the video in a second, and let's say that I'm going to kind of like erase this one. Now let's move it over, and we'll put it right here. Okay, we'll still call it force 2. This distance will be literally 0.5 meters. Figure out what size force 2 now has to be. And I'll give you a hint. It's going to be much larger in order to support this beam so that it doesn't move at all. And by the way, we will keep this force now at 4 newtons over here. So this term will be the same, 12 newton meters over here, and now we're kind of playing around with this term. All right, so pause it and see if you can figure it out. All right, well, I've done the math over here. The torques must sum to 0. And they do, but only if force 2 ends up being negative 24 newtons. We need to cancel out this positive 12 newton meters of torque with negative 12 newton meters of torque. And if you're half of a meter away, then the math works out to be a very large force of 24 newtons, 6 times as much. So I've kind of drawn that here. I don't think I got it exactly right, but this arrow should be 6 times as long as this other arrow over here. Great, and then you can also realize that in terms of distance from point P, can you figure out why this number 6 is showing up? Think about it. Look at how far away force 2 is compared to force 1. Force 2 is 6 times as far away. So it can be 6 times as less in terms of its strength, whereas force 1 is 6 times closer, so its force must be 6 times as great in order for everything to balance out. So it doesn't rotate at all. All right. Now, there's one more little subtlety about this problem that maybe some of you have noticed, and I left something out kind of deliberately on purpose that we technically actually need to take care of in order to do this analysis correctly. I'll give you a hint, and the hint is that upon the application of these two forces, force 1 and force 2, the beam is absolutely going to be at rest. Okay, So the beam stays at rest the whole time. Put a big box around that. All right, well, if that's true, then if you just look at this picture, and let me help simplify it for you for a second. I'll just draw it smaller down here. Here's what I'm telling you. We've got a force like this, 4 newtons, and then a force here of 24 newtons right now. This beam would not rotate, but there's a big problem. Can you figure out what's happening here? Look, I'm claiming that the beam is at rest. Pause the video and see if you can figure out a problem that we need to take care of in our analysis. Go ahead, pause the video. All right, well, hopefully you saw it. And we're getting to now, formally, the 2 conditions that are required for static equilibrium. Number 1, or I guess number 2 over here on the right, is that the sum of the torques must equal 0, or balanced torques. And that works. That we proved that mathematically over here. But what about Newton's second law? Sum of the forces, well, that still has to equal 0 on the beam, and it's not doing that right now. And that should be totally obvious to you. For example, if we add all the forces up, well, sum of the forces equals, well, we've got this 24 Newton force, negative 24 Newton force pulling down, and then we've got this 4 Newton force up. That doesn't work, right? That's negative 20 newtons of force, and we should therefore see the center of mass of this object accelerate down, which it's clearly not doing. So how do we get out of this kind of puzzle? I'll give you a hint. There's an object that we haven't really talked much about, another object in this question that must be exerting a force. What do you think it is? Pause the video and figure it out. All right, well, I hope you said hinge, and that's most definitely what it is. The hinge must be applying a force. How much force? Well, let's figure it out. We can write down a term here called the force of the hinge. The hinge is in contact with the beam, so it applies a contact force. Remember, we're ignoring gravity too, by the way. We'll ultimately bring that in some more challenging problems later, but for now we're just ignoring the force of gravity. And so we have 3 forces, F1, F2, and then the hinge force. And if you just look at the situation, all of this must equal 0 if it is true that the beam is not accelerating linearly. Therefore, the force of the hinge must be 20 newtons, positive. Great. But now, okay, this is where it gets kind of crazy. Now, okay, let's draw that in, and you might be logically shouting out loud, wait a minute, oh no, we've got a third force? Does that mean our torque analysis was wrong? Because when we did our torque analysis, we summed up all the torques, and we did torque 1 plus torque 2, and we were all happy, right? Dot, dot, dot. We plugged it in. And there was something I didn't tell you at that time because I didn't want to complicate things at that moment in the beginning of the problem. And yeah, I mean, technically we forgot something because every force that exerts on an object, for every force that exerts on an object, you can calculate a torque for that force. Sometimes it does produce a value like we've seen, but other times it's 0. So to be more technical, let's actually write out the sum, and it should be, well, we now have a torque from the hinge that we have to write down, plus torque 1 plus torque 2. Every force that you identify, you have to then also write down a term for a corresponding possible torque. Okay. All right. Now, if we just kind of check these off, we know this is going to produce a torque. That's going to produce a torque about point P. Actually, let's be real specific. About P, and then over here as well, the torque of the hinge about P. All right. But now, hopefully, you can kind of get out of this conundrum pretty easily. Think about, well, how would we calculate the torque by the force of the hinge exerted on the beam about point P. Kind of like a long sentence there. Um, Pause the video and see if you can figure out numerically how much torque does the hinge apply to the beam. Go ahead. All right, well, hopefully you got it. And you can see that there is no way you can draw a straight line from point P to point P. Like you're right on the point. So R is equal to 0 for the hinge, and therefore 0 times any amount of force here is going to give you 0 torque at point P. All right, so that very conveniently allows us to come over here and just cross that out, and this goes to 0. So back to taking a final step back, and if you just think about the steps on how to calculate torque, 1, 2, 3, 4, that we talked about in the beginning of the video, pick a point, right? Any fixed point in space. Well, you can see how the choice of that point is important because sometimes a clever choice of that point allows a torque value to actually end up equaling 0, and it makes the math a little bit easier in that case. And so that's happening here in this scenario. All right, I want to finish this video with kind of finalizing something about torque and the vectors involved, specifically the position vector r and then the force vector. I had a couple other little formulas written down early in the video that we didn't really go into talk about. And I want to just show you something about that that's important. So here we have a mass m, and there's a force being exerted to the right on this mass. And then I have selected point P up here. I put a little X for the point, and then I labeled that point P. And let's calculate the torque about that point that this force exerts on mass m. And notice that this is just a point particle. In fact, like the point particle is not even going to move in a circle. It's not going to rotate in any way like as you think of rotating, right? It's just going to go straight and speed up to the right. However, there still is this thing called the torque about point P that exists as a mathematical thing that can be used. So let's learn how to calculate that. I mean, we already know the steps. Just draw a straight line or a position vector like this. Oops, a little bit off. There we go. And there's the position vector r, and then we have the force vector f. And the way to talk about that angle, so when we write down, there's a couple ways to do this. R times f perpendicular, that's one way to do it. Another way is r f sine theta. You'll often see that on formula sheets and written down a bunch of places. It's the same thing, really. It's picking out the perpendicular component. That's what the sine of theta is doing. It's just that sometimes you can confuse yourself with what angle are they talking about there with theta, and you have to slow down and figure it out. So in situations where it's kind of looking a little weird like it is here, you can take the two vectors, r and f, and I'll draw them out, and just put them tail to tail. So there's r, and then f is like this. All right, tail to tail. And when you do that, this angle is theta, the angle between the vectors. All right, so we'll just write down here, this is the angle between r and f when placed tail to tail. Cool. Now to determine the direction and to know that in this case, this torque in terms of its direction would be a counterclockwise torque. It's kind of hard to see that, I think, when you're just looking at this image of the vectors drawn out over here. So like, how is this causing a counterclockwise or positive torque? And that comes from just the more formal definition of torque with math, and it's really what's called a cross product. It's a mathematical operation that's a little bit more sophisticated than just regular old multiplication. And when you multiply two vectors in this way, doing what's called crossing the two vectors via the cross product, you produce another vector. So torque is a vector. It has a direction associated with it. R is a vector and F is a vector, right? And so um, the way to get the direction about that new vector that is produced, meaning what's the direction of the torque vector, you do what's called crossing the two vectors. And the first thing you do is you draw them tail to tail, like we've done here. And then you go R cross F, R cross F. And you can kind of see that here, how this arrow kind of goes counterclockwise. And the way you imagine it, you can use what's called the right hand rule. So this is the right hand. And what you do first is actually this bottom picture, is you point your fingers parallel to R. I've kind of tried to show that here. So your fingers point down parallel to R. And then you keep your thumb at a right angle to your other fingers. And then you curl, or cross as it's called, in the direction of the force. So you can kind of see that here. My fingers are pointing down and to the right, and then I'm going to curl my fingers up in the direction of F, and then your thumb actually points out of the page, coming out straight at you. You know, it's kind of hard to see that here because we're looking at a two-dimensional plane. But just imagine like an arrow literally coming out of this page, coming towards your face. And one way to actually denote that is with a circle and then a little dot. And this would be out of page. It's kind of like the tip. Like imagine there's somebody inside of the piece of paper who has who's going to shoot an arrow at you, and it's going to come out of the page and literally like hit you, right? Well, as it's coming out of the page, you would see the tip of the arrow come, towards you. And so that would be the direction of the torque. It's in the third dimension. So we have like two vectors, R and F, right here, that are in two-dimensional space in the plane of the paper, and then the torque vector technically is coming out of the page. And that would correspond to counterclockwise. Which means, of course, that if it was going into the page, and then by the way, that is represented by an X, into page, this would be a clockwise torque. Now, luckily for us, like I've said before, we don't have to really get that bogged down in this, three-dimensional vector idea and doing cross products. I'm telling it to you here just so you're kind of aware of it. It's helpful, especially when we get to talk about angular momentum and some more complex systems. But for our purposes in solving problems, the plus and minus sign is going to be enough to solve those problems, and then just generally understanding counterclockwise and clockwise will be needed as well. But you can see how this mathematical formalism, I hope, is a little bit helpful to give you an exact procedure so you can always figure out the direction of a torque using this right-hand rule, even if the picture looks kind of complicated, as opposed to the pretty intuitive type of thing where you have a beam and a pivot, and you're like, okay, so is this a counterclockwise torque or what, right? And most people are able to kind of easily see that, yeah, it's counterclockwise because I guess it goes up, right, and spins this way. But a situation like this is a little bit more abstract. So, all right, there you go. Kind of a nice introduction to how to calculate torque, what static equilibrium is, what torques cause, if there are non-zero net torques, meaning angular acceleration, etc. We're going to go a lot further with this idea, but hopefully you got something out of this video and you're ready to solve some more advanced problems. All right, we'll see you later.